Bing, bing. And connect. What are you looking for? I know. All right, so a little bit smaller screen. Sorry, I'm in full screen and stretched as far as I can go here. So 3 is measurement. We got to get through 3 and we got to get through 10 before the semester. And that should be pretty doable because 3 is fairly short. But as you learned, it's just a lot of definition. It's got a lot of vocab. Are they what? Probably not. I don't know yet. I haven't finished up the last test. I got to finish up this one before I can plan the next one. No. No, don't just reuse them. They're out there. They're out there. Those were available yesterday. All right, so let's talk measurement. We haven't done any numbers yet here. So now the next 2 units, heavy numbers. You need your TIs. Make sure they're charged, please. All right. We're going to be using them a bunch. Not so much today, but you will need them tomorrow when you get to the worksheet. Okay. Measurement means we're going to have a quantitative side of it. We call this an observation. Bless you. Huh? And/or qualitative. Okay. I'm going to tell you. Yep. Quantitative is just going to be a number. We're going to measure things in terms of grams, mils. For the most part, that's what we measure in here. Grams and milliliters. That's about it for the most part. Pardon? Yeah, there's new TLCs over there. Qualitative is going to be things like color, texture, and quite often in here, smell, odor. When we measure something, 2 of the vocab words you probably got to were accuracy and precision. Accuracy is very simple. It's the closeness to a known value. For our purposes, I know we all want to be perfect. We want to have 100%. We're going to accept closeness to being within 5%. So 95% accurate is going to be good enough for our purposes. You go into the laboratory situation, those tolerances go up. Start becoming an engineer, your accuracy is going to go to probably 99.9999% accurate. But for us, 5% accuracy is going to be just fine. That means you have to know the value before you can tell whether you're accurate or not. Am I right? I don't know. I can't tell if you're right until I compare it to a known value. I can't grade a test until I make an answer key. Basically. Precision is easier. Precision is repeatability. In this case, it's the closeness or grouping of values. The key here is you got to have multiple measures. And we could talk a lot about real life things and precision, people shooting free throws. I am sure if you have a chemistry book, there is a picture of a dartboard. There will be no dartboard questions on the quiz or test. That much I do know. But let's talk about numbers because we are going to weigh things in here. Excuse me. We're going to mass. We've got balances out there. So suppose, put this in green and say, given a 50.00 gram weight. We know that, it says it on there. And we do 3 trials. Trial 1, trial 2, trial 3. So we know we can have some discussion of accuracy and precision. In the first trial, we weigh it 3 times, mass it out. 50 grams, 49.85, 50.11. I'm going to call trial 1 accurate and precise. Numbers are all tightly clumped, and the numbers are all very close to 50. We like this. Now let's look at trial 2. 32.18, 32.20, 32.10. All of those are in grams. No accuracy. We do have precision. And we're going to say, whoops. Precise, and we're going to throw an asterisk number 1 in there. And I'll explain my asterisks in a second. Trial number 3 comes around and we mass it out. We get 50.90, 49.50, looking pretty good, 31.30. This one's going to be neither accurate or precise. And of course, you know, there's going to be an asterisk. So accuracy and precision were 2 vocab terms that you guys had. Trial 1. Everybody good? We're accurate, we're precise. Yeah, we're okay there. Trial 2, we can see we're precise, but we're not accurate. So what does asterisk number 1 mean? Asterisk number 1, we would call systemic error. And what that means is there's a procedural problem. This is going to be error that is repeatable every single time. So in our case, where we're massing something out, this one could be explained real easily. Someone used the mass before us, put it on, hit the tear button. So when we went up to read it, we looked like we were measuring from 0, but we weren't measuring from 0. We were measuring from something somebody else had already put on there. And that messed us up. It's going to be the same direction every single time. It's something wrong with the procedure, what we're doing. Okay. Error number 2 is something we're more familiar with. This is going to be random error. This is an error in carrying out the procedure. The procedure was okay, but we made a mistake. Most commonly, this is human error. Other things that could be random error. I masked out the right stuff, but I spilled it. That's like the classic AP question. You know, a student performs a lab experiment, spills some of their stuff after they masked it. What would you expect this to do to their results? Explain. Yo.
So why would the second one be precise error and the other one be like the other one?
The other one is precise because all of my numbers are really grouped tightly together. And because they're all off about 18 grams, we know there must be something wrong with the measuring device or the procedure of measuring. Whereas this one went, I'm doing pretty good in the first two trials here, but then the third one went way down. And if we wanted to make this even more, we could say, hey, this one went up to 70. And now we have error that's high and error that's low. And we've got a bunch of different. So that's my error thing. No dartboards, but how close is our data? Is it repeatable? Come on.
So why would the first one, the first answer is not random? Wouldn't it be their fault that they didn't, like, you know, that they didn't check the scale comparison?
In trial one?
Sorry.
In trial two, why wouldn't it be random? Because it's always repeatable going in the same direction. We're getting precision because we have multiple measures that are doing the same thing. It'd be more random when it goes up, down. Okay. Then we get numbers. Scientific notation. Come on, Steve. Scientific notation. This one was messed up in the book, right? If you tried to read it, it said all sorts of really, but we all know what scientific notation is. It's basically, it's raising a number to an exponent of 10. It represents large or small numbers. I don't have much more on that. You guys did scientific notation in 6th grade. You've done this. Ooh. It's just not chemistry without red. Red asterisk in a box. If you write a number, write a unit. Every number must have a unit. Always, always, always. Makes it easy to give partial credit that way. Okay. Big topic. Significant figures. This helps us answer the question of how many numbers do you want us to round to? So we don't have to answer that. We can know. All right. Significant figures. All measurements. Have uncertainty. So we can record all the certain digits then estimate the last. Here's what I mean. I apologize, I'm going to draw. Big blow up. Jennifer, what's the volume in the thingy? Okay, how many digits are we sure of? We're sure of 54, right? So we get to guess one more digit. We get to put one more in. If it's dead on the money, put a 0. So if it's calibrated to the mill, estimate the tenth. We can do this, right? Woo. One, 2, 4. Shay, what's the volume in the thingy? So which ones are we sure of? We're sure of 2.1. So what's your estimated? What? 6. 6? 6. I'm never going to question whether that's a 5 or a 6. I'm never going to come up to your glassware and go, wait a minute, that might be 2.14. I'm more concerned, are we getting the right number of decimals off of whatever glassware we're using to measure? That's the important thing. We always get to estimate one more. And those are the two volume situations that you guys should be in. So here it's graduated on the left, it's graduated to the milliliter. So we get to estimate a tenth. On the right, it's graduated to the tenth of a mil. So we get to estimate 100th. Super easy. Same thing goes with rulers. You guys are measuring something with a ruler, it's graduated to the mil. You get to estimate one more on a ruler. But we don't do that. This is what we basically do. Our balances are digital. The uncertainty is already built in. So you don't get to add another digit on those. Whoops. Okay. So rules for counting Sig Figs. We just measured Sig Figs. Now we're going to count Sig Figs in a problem. Then we're going to do calculations with Sig Figs. It'll be fine. Think. Rule number one, all non-zero integers are significant. So 7.3651. That's got 5 sig figs. Yo,
Is it called six figures? Because it's significant.
significant figures, we shorten it up to sig figs. SF. Some books even use the term significant digits. The rest of the rules are zeros. Zeros are weird. Why, what? Why would it have 5? There are 5 digits there. Hang on, let me. 5 significant figs. Sorry. There we go. So there might be some where it's just like, hey, how many sig figs are in the following number? Boom, count them up. We like these. Sandwich zeros are significant. Here's what we mean by that. What are they sandwiched by? They're sandwiched by integers. They can also be sandwiched by a decimal. Three, 5, 3. There's zeros that are in the middle of a number. They've been measured, so they're accurate. They're significant. They're important to us. Three are called leading zeros. These kids are insignificant. Matter of fact, you don't even see me write leading zeros. These are the ones that are 0.0123. These are all the zeros that come before the number actually starts. The number hasn't started yet. The number doesn't start till we get to the integer. So that has 3 sig figs. That only has 2 sig figs. So leaders are easy. They're useless because I could account for those with exponential notation. See, we look at the 0.000046, and that looks kind of weird. Well, what if we just wrote that 4.6, 10 to the negative 1, 2, 3, 4, 5. Boom. Same thing, same number. Okay. 4 is trailing zeros. 4 and 5 are trailing zeros. First ones are going to be left of the decimal. These are going to be significant with when there is a decimal. These are insignificant without. So 100 point has 3 sig figs. 100 has 1 sig fig. These are only ones to the left of the decimal. We're gonna do right of the decimal next. Four doesn't come up very often. 5 comes up a lot. Trailing zeros to the right. These are big time significant. So 2.50. 2.50 is 3 sig figs. That zero is significant. All of those are significant. In my bottom, I got 5 sig figs. Those are all significant because the 5 is where we start. The 0 here between the 1 and the 2 is sandwiched, and the 2 and the 0 is trailing to the right. See, mathematically, you're absolutely right. But measurement wise, we have our dandy dual pan balances. The big side of this measures to the grams. I can buy a gram balance for $12, super cheap. I want to get a centigram balance, 2 decimal places. Now the price went up to about $100. When I want to start getting accuracy, I want to be able to count those zeros to report that level of accuracy. Then I have to have a more accurate measurement device. Mathematically, it's still the same, but measurement-wise, it's a big difference. We're measuring that 0. And usually we have to pay a lot of money to measure that 0. To get out to a milligram, but you're right. Is 2.5 the same value as 2.5? Yes. Mathematically it is, but measurement wise, we're getting more accuracy. Okay, fair question. Last one. And it doesn't even get a number. What? Correct. Because I could just as easily write this as 5.1020 times 10 to the negative 4th. Counted numbers are exact. What we mean by that is they are infinitely significant. One, two, three, 4, 5, 6, 7, 8, 9, 10. There are 10 students in this room. That is a counted value. It's not measured. It is exact. It's infinitely significant. I know I'm accurate. I know I'm perfectly correct here. Now that's nice. That's if we're just counting them up in a problem. But when we're doing problems, we're going to do computation with them. So now we got to do calculating with Sig Figs. This is what part of your worksheet is tomorrow. What we do? 9:04. We're doing great. Let's start with the easy one. There are 2 rules. There's a rule for multiplying and dividing, and there's a rule for adding and subtracting. We do a lot more multiplication and division here. Here's the rule. Your answer, so we're not going to ask how many places do you want us to round to? Your answer can have as many sig figs as the least number used in the problem. So if we have 1785 grams, say we measured something out, we're going to do a density problem, 2.13 centimeters cubed. And I put that into Texas Instruments. TI says 8.38028 grams per centimeter cubed. Stevie, how many sig figs in 1785?
Oh,
No. In 1785, there are 4. How many sig figs in 213? Which one's smaller? 3 is smaller than 4. Stick with me. So my answer can only be 8.38. And we'll round. Don't truncate. We'll round to make that work. Yes, not the value, but the smallest number of sig figs. Multiplication division is easy, and that's what we do most of. When we do have to add and subtract, the rule's a little bit different. Your answer can have as many decimal places. Now it's not sig figs, now it's decimal places. As the least in the problem. Here's what we mean. $12.3, and we're going to add to that 4.27. Texas Instruments spits out 1657. But I can't represent that level of accuracy because I only know my accuracy to the 10th. So the best answer you can put is 16.6. Say that again, I'm sorry. Round it down, 16.4. No, we did already talk about this. 45 rounds down. If you have an 89.45, it's an 89. It's not past half. Pretty much past half, but not past half. What? Sure. Mhm. Oh, yeah, if we had, that's a neat one. If we had 12.3 plus 4 point, well, no, sorry, here, let's do that. Let's make that to 0. 12.0, 4.27. And now you get 16.27. And we got to make these centimeters. That 0 still counts. So 16.3. Absolutely.
And also, why does, like, so like, for the rule of
Mhm.
can you explain the decimal?
Decimals provide accuracy is the best way of explaining that. The decimal means, what this decimal means is when I write this number, I'm 99% sure that my number's between 99 and 101. Because it's the last decimal it's the last digit that's uncertain. These aren't digits, they're not certain. So when I write this, the only certain number I have is the 1. My number here is somewhere between 0 and 200. That decimal provides accuracy. It counts. It's a big deal. Think of it in terms of my balance again. I'm paying for those decimal places. Okay, Sig Figs, and there's going to be a section on your worksheet tomorrow about that. Does today pretty much feel like 6th grade, 8th grade over again? We did a lot of this stuff in 8th grade. Well, I'm sorry, we're going to do it again. 6th grade was fun. The best 3 years of my life. Ooh. Did not dig 8th grade. SI. So System International. Now we're going French here, kids. We will measure temperature. We've got thermometers. Please never use them in Fahrenheit. There's a button that says F and C. Always measure in Celsius. Always measure in System International. There are base units to System International. This is a trick question. The base units are meters, seconds, and for mass, it's kilograms, not grams. That's a classic trick question. Don't fall for it. No. I'm going to talk about liters in a minute after I do my prefixes. We need to know prefixes. I don't really know why we need a mega, but we're going to do it. Kilo, hecta, deca. There's your base unit. Gets smaller, we go deci, centi, milli. What's after a milli? What? Micro, nano, pico. So if a base unit's 1, a deca has 10 base units. A deci has 1/10 of a base unit. A centi has 100th. A milli has 1,000th. A micro, I'm going to 10 to the minus sixth. A nano is 10 to the minus ninth. And a pico is 10 to the minus 12th. Pardon? Mega is a million, 10 to the sixth. Million. What's bigger than a mega? You know this. Giga. What's bigger than a giga? Terabyte. You know this because of computer storage now. There's something bigger than a tera. I don't remember what it is. It's that we don't need one. And we don't need one. Those are our prefixes. Okay. Shay said, what about liters? Liters aren't a base unit. Liters are considered a derived unit. A derived unit can either be a combined unit or it can be a unit that is squared for area or cubed for volume. So a decimeter cubed is a liter. 1 centimeter cubed is 1 mil. And for the doctor folks out there, they call them cc's. Cubic centimeters. Memorize those. They're nice to have. We're killing it, kids. We're gonna make it. We're gonna make it with a bonus. I know, and you guys are being great. I appreciate it. We're covering a lot of ground. But those of you that are showing up tomorrow, you have nothing to do but a worksheet. Ronan, you putting in a Friday this week? Oh, boy. All right. I will be too. Oh, thank you. That's why I can't hear anything. Now we're good. Last topic. Back to 8th grade. I know they taught you this. Dimensional analysis. We love this. This is a method of solving problems using conversion factors. We'll give you steps, but I think most of you already know how to do this. 1, start with the given in the problem. This is a huge number. This will determine your Sig Figs. 2. Set up your conversion factor. So your units, I'm huge on units. Your units are going to cancel on the diagonal. Yep. It works. Just trust the process. Place a 1 with the bigger unit, the bigger value. On the conversion factor. Four, multiply, divide. Calculate the answer. Five, apply Sig Figs. Now that's a lot of writing. The problem's actually easier to do. We kind of have to. Kind of have to. So the steps take longer to write than actually doing the problem. The problem's not hard here. Let's do 3 examples. Then bonus. Convert. Whoa. Put down here. 2.63 meters to micrometers. So that's what we're given. Start with 263 meters. Set up the T-charts. Show all work for credit. I will be very, very generous in partial credit if you guys can set these up and show me what you're doing. If you get the wrong answer, you can get, 3 or 4 out of 5 points just by setting up work. It's worth it. Okay, so we want to get meters on the bottom. We want to get micrometers, rut-row. That's a symbol for a micrometer. That's a micro. It's a lowercase Greek mu. Which one's bigger, a meter or a micrometer? Put a 1 there. How many microns are in a meter? So if the meter's bigger, there's always going to be a positive here. We're never going to need, as long as you put the bigger number, the bigger value is 1, this will never be a negative exponent. So you never worry about sliding the wrong way. This works. Multiply it across, and this one's super easy. 263, 10 to the 6th micrometers. Put a box around that. Teachers love that stuff. Pardon? Nope. Because up here, what we said was, what do I do here? 1 micrometer is 10 to the negative sixth of a meter. So 1 meter is 10 to the positive 6 micrometers. Yep.
That's a million.
Those are millionths.
Nano is billions. Pico is trillion.
Convert. So if you haven't figured out, there's a lot of open format in this chapter, which means a lot of partial credit. Like that. Convert 747 nanometers to kilos. In this case, we're crossing over, so you have to go to the base unit. We're going from really small to the base to really big. So it's going to take us 2 steps, kids. In the first one, let's go from nanos to base to meters. 1 meter, 1 times 10 to the 9th nanos. Then in the second one, go from meters to kilos. Kilos bigger. Give me 2 steps. I can give you 2 points. Show all work for credit, please. No more sliding. And you'll understand why when we get to unit 10. You won't be able to slide. Three, last example. Convert 95 meters per hour to centimeters per second. So this is one of those derived units. Got division going on here. Just write it out. 95 meters. Don't do the diagonal thing either. Put the hours on the bottom. Which one do you want to do first, meters or hours? Too late, she was faster. Let's do meters to centimeters. Which one's bigger? How many centimeters? 100. So just like those polyatomic ions, you need to know those dimensional, those metric conversions. You got to know there's 100. You cannot slide. You will not get any credit for sliding decimals. The directions will say, solve the following problems using dimensional analysis. Trust me, we need to use it later on. Okay, then hours to centimeters. I got to get my hours there, or hours to seconds, excuse me. Let's go hours to minutes. Then let's go minutes to seconds. You can go, this is one of those where if you want to go direct from hours to seconds, but I've seen too many people mess that up, including myself. 1 hour is 60 minutes and 1 minute has 60 seconds. An hour has 3,600 seconds. We know that. Multiply it top and bottom, divide it on out. 95 has 2 sig figs. So my answer is going to have 2 sig figs. And it's going to be in centimeters per second. And that gets us sig figs, measurement, dimensional analysis. Yes. Poof.